From the South Studios of Way Happy, this is Mr. Meyer, and we are doing 9-1 Basic Combinatorics. Go ahead and just say, woo, this sounds like fun. And it is. We are going to talk about counting. You've been counting for many, many years, and we're just going to make sure you know how to do it. So sometimes it can get a little tricky, and there are different types of counting, and let's see. So we will be counting, arrangements of things, lists of things, possible outcomes of things, and kind of down here you can see that sometimes a tree diagram is a really good way to count stuff. You just kind of think of each option and you keep doing each tree until you've picked out all the options. And so we will probably see those once in a great while, but they're usually my last ditch effort, like the thing I need to do when I'm really confused on a problem. So let's start off with the multiplication principle of counting, or also known as the counting principle. And what it is it just talks about that, making a tree diagram might be too big, and so the way we could do this is kind of shorten it out. And if you look at my first example here, we will have license plates. So we are making some license plates, and we want to know how many different license plates can be made. So how many cars can we actually have on the roads? And we have a strict rule in our license plate world, or in our world of wherever we are, that says a license plate must have 4 letters. It must have 4 letters. 1, 2, 3, 4 letters. My boxes represent letters. And then it will be followed by 3 numerical digits. So a digit, a digit, and a digit. And so what the counting principle says is I want to go ahead and try to figure out how many different license plates there are. And what you do is you just sit down and you find out how many different values there are for each of these boxes, and then you multiply it together. Plain and simple. So if we're allowed to have a letter, this is a letter, this is a letter, this is a letter, this is a letter, then this is a digit, this is a digit, this is a digit. There are 26 letters in the alphabet. There's no restrictions on the letters. So then after you picked your letter, you picked whatever you did, maybe M for math. Then your next letter would be, you have 26 options again. And then your next letter, you have 26 options again. And then your next letter, you have 26 options again. Now that's how many different ways you could have letters. So you could have MATH would be one of those ways, but how many ways are there total? Well, there's AAAA, and there's AAAB, and there's AAAC, and we could be here a long time doing this. So that's why a tree diagram might not be all that fun. Then you get to put a digit, and a digit is 0 through 9. So there's 10 digits. So you have 10 digits and 10 digits and 10 digits. So holy macaroni grill, when you go to do this, you've got 26 to the 4th. Where's my 4? To the 4th times, what is that, 1,000? Easier. And so look at how many license plates. 4, 5, 6, 9, 7, 6. I already forgot it. 4, 5, 6, 9, 7, 6, 0, 0, 0. Let's hope. 4, 5, 6, 9, 7, 6. Beautiful. There it is. That's how many license plates. And now, as the people of Way Happyville, we know that we can at least make that many license plates. So that's how many cars we're going to allow, or how many cars and trailers and whatever in our Way Happyville before we run out of license plates. You could do the same thing with phone numbers. You'll start to understand why we have area codes, and you'll start to say, like, wow, we've used up a lot of phone numbers with cell phones and home phones and everything. All right, back to license plates. Really interesting on the counting principle is what would happen if we couldn't repeat the letters. Like you couldn't have A. They're like, nope, once you use the A, you've used your A, and that's it. So you just got to make sure that you take that into account. So again, you have 4 letters, and then you have 3 digits, but no one is allowed to be repeated. So if you use an A, it's gone. So that first letter, it's up first. You get anything you want, but now you've used M. So when you go to your next letter, you are no longer allowed to use M. You only have 25 options. And then you go to your next letter, and you've now used MA, so you can't use those. So now you only have 24 letters of the alphabet you're allowed to use. And then 23. And same thing with digits. Maybe you used that number 4. So you had 10 options for that first one, but now that you've used the 4, Now you only have 9 options, and then you only have 8 options, and you would multiply this all together. And I was trying to come up with something like math for life, but it obviously didn't work. And so now I go ahead and I just go, 26 times 25 times 24 times 23 times 10 times 9 times 8. Thank you, Sheila. And now notice, if we don't let people repeat, we lose a lot of cars, right? And a lot of trailers and everything else. So that would be our answer for if we did not let anyone repeat. 258-336. 258-336-000. And there you have it. Now these are called permutations. All of these different license plates, there are this many permutations of a license plate given our restrictions. There are this many permutations of this license plate given our restrictions. And so permutations are just a fancy thing to do to find out how many different ways something can be arranged. Now there's also little things about permutations like factorial that are usually exciting. How many ways can you arrange the word computer? So I give you a word. How many different ways can you arrange an 8-letter word? So you have, again, 8 spots. First letter, second letter, third letter, fourth letter, fifth letter, sixth letter, seventh letter, 8th letter. How many ways can you arrange it? Well, your choices for the first letter of computer, there are 8. Now you've used something. I don't know, the M. And now how many do you have for the second? Only 7. And you used the P. And then now you're like, oh, I don't know what letter to use next, right? Well, you only have 6 choices because you've used up some, and then 5, and then 4, and then 3, and then 2, and then 1. And we multiply all this together. But this has a fancy name if you go all the way down to 1. We can call this 8 factorial. Factorial means that you're going to start with the number 8, and you're going to multiply all the successive numbers all the way down to 1, and then that's your answer. So you have an 8 factorial. Now the cool thing is your calculator has a factorial button, so you don't have to push all those buttons. You hit 8, you go math, right here's the math button, go over to PRB, which is probability, and press number 4, and you hit enter, and you got 40,320 as your answer. And that's how many ways, that's how many different arrangements you can make from the word computer. Now if you get bored, try to write them all out. But that is how many arrangements you can make with the word computer, believe it or not. So when you're playing Scrabble and you have those letters, well, there's 40,000 different possibilities to lay out those letters. Now, the one thing I want to mention before a question is, what if, and this is the special part of the special permutations part, sometimes letters repeat like the word success. And that makes it just a little bit different on how we have to count it. Because again, you have 7 letters this time. So you would think, oh, it's 7 factorial. But you got bad news. You got 2 C's. So you have to divide by those because you can't tell them apart. And you have to divide by 2 factorial because, again, they can go in any order. And notice we have, oh my gosh, 3 S's. So I got to put that in the denominator of the 3 S's. And then nobody else repeats, so I'm golden. This is now ready to go. So, you know, and if you don't have a calculator, it's always fun to 7, 6, 5, 4. Okay, this is not going to be fun. 2, 1, and on the bottom here I have 2 and a 1, and then a 3 and a 2 and a 1. So there's your 2 factorial, your 3 factorial, your 7 factorial. You'll notice some things cancel. The 2 could go into here 2 times, and look at that. You have 42 times 10, or 420, and you jump up and down. Yay! I got the answer! Again, you could do your calculator button and use parentheses in your denominator, or use your fraction button. All right, let's ask you a little question about a permutation, and then we'll come back and talk a little more about permutations. Nice job. All right, let's talk a little bit more about permutations. Now, permutation, you start at the number and you go all the way down to 1. Well, what if you don't wanna? Like, what if that license plate problem, there was 26 letters and we didn't go all the way down to 1 because we didn't have 26 spaces on the license plate frame to put every letter in the alphabet. We only had 4 letters. So that's where this special permutation formula comes in that says, hey, look, I want there's n things possible, but I only want to choose r things out of that group. So r is a smaller number, n is always the bigger number, and I'm picking r things out of a group of n. And to do a permutation on that, I have a little formula, n factorial over n minus r factorial. Beautiful. Your calculator even has this button. So how do I use it? Well, I use it like this. I have 12 skiers, and they're going to the Olympics, and they're going to compete for gold, silver, and bronze. So how many permutations can I make? Well, I want to pick 3 skiers out of the 12. So how many ways can I pick those 3? And their order actually matters here because it's different if you got the gold or the silver or the bronze. I might take Han wins the gold and Mr. Avila wins the silver and Mr. Feliciano gets the bronze. What if we do it again and these 2 guys switch spots? Well, that's a different permutation. So then that would be a different outcome with Mr. Avila getting the gold and Mr. Han getting the silver. So I got to, count all these different ways. There's a lot of ways, right? I only picked 3 people and we have 12. So the way you could figure it out is you could sit there and tree diagram every outcome, right? There's a chance that Han wins and then Avila and then Feliciano, or there's a chance that Han wins and then Feliciano wins and then Avila, or there's a chance that Han wins and then we'd have to do this constantly and your tree would get out of control and you would cry, but you could totally do it. Or you could just I have 12 skiers and I want to know how many outcomes for 3 of them to be chosen. And so I just use my formula, 12 factorial over 12 minus 3 factorial, which turns into 21 factorial. Nice. 12 factorial over 9 factorial. Now here's the cool part. 12 times 11 times 10 times 9 factorial, all over 9 factorial. Boom, boom. This is really just 12 times 11 times 10. Again, I said you could do it on your calculator, so let's scroll over and get Sheila here and say, all right, Sheila, we're going to type in the number 12, and then we're going to hit math, go over to probability again, and look at number 2 is NPR. And then we put 3, and it says, hey, there's 1,320 different ways to arrange 12 skiers into medals. So that's kind of cool, right? Just it seems like a lot of ways, and I'm always like, what? And then I try to figure them out, and then I find out that there is a lot of ways, and I start to cry and say, I wish I wouldn't have tried to figure that out. What about combinations? There is also this beautiful thing called combinations. And combinations are a whole lot like permutations, except for one thing. In a combination, the arrangements don't matter. The order doesn't matter. In other words, that Han Avila Feliciano and the Avila Han Feliciano, a combination says, hey, that's the same 3 guys, so I'm just going to count it once. So it would only see that as one outcome. Why? And the same thing, Feliciano Avila Han, it would say, that's the same 3 guys, so you haven't changed anything. So a combination will say, hey, look, anyone that has the same 3 guys, I'm just counting that once and one time only. So order doesn't matter, that the way they finish or the way they're picked or the way they're selected. So those would be called combinations. And it has its own formula too. Notice it looks like the permutation folder right there, formula, but it has that little r factorial on the outside, which is just it divides out all the ones that are repeaters. So that will take care of our combination. So how many different 5 hard cans can be dealt from a standard deck of cards? So I have 52 cards, and I need to deal out on these 52 cards. I am dealing out 5. So 52 C for 5. Sorry, was thinking there. So I have 52 cards, and I am dealing out 5 cards, and that's how many different combinations I could make. And so I'd grab my calculator and power that in. And then how many of these different cards could have the same suit? In other words, a flush. And a flush is 13 combination 5. How many ways can I pick 5 of the 13 cards? There's only 13. I was thinking that you may not know cards, and probably will like to use card questions, so we're going to have to discuss these in class. But there are 4 suits. 2 are black, 2 are red. There are 13 cards in each suit, and so there's 26 red and 26 black. And a flush means that they're all the same suit, so that means all 5 cards would have had to come from one suit of 13. And there's 4 different sets of those, so you would actually have to multiply this outcome by 4 to see how many different flushes you are, because are you talking about a hearts or diamond or spade? And again, this is where counting kind of gets confusing now, so we got to be careful. So when you're picking a group from a group, you're going to use combinations or permutations. If order doesn't matter, use combinations. If order does matter, use permutations. And that's going to be the really confusing part, like right here. Again, a little difference between the two is explained there, but more importantly, you want to know, you go to a pizza parlor and they have 10 different toppings. How many ways can you pick 4 toppings? Well, you're picking a group from a group, so I'm pretty confident that it's either 10P4 or it's 10C4, and that's usually where kids will get confused. You got to decide, does the order of the toppings, now sauce and cheese are already on there because that's a pizza, so the toppings, pepperoni, mushrooms, olives, whatever, does it matter the order they put them on, or would it be the same pizza, right? So if I put pepperoni and then olives, is that a different pizza if I put olives and then pepperoni? No. So I don't think order matters, so I'm going to say combination for this. Get my calculator and I'm going to type it in. How many ways can you pick 3 people, 1, 2, 3, out of a 25-member group? Well, again, I'm picking 3 out of a group, so I'm going to do 25P3 or 25C3. I don't know which one yet, but then I decide, does order matter? When you pick a president, a vice president, a secretary, does the order matter if I mix those 3 people up? And just like the Avila Feliciano Hahn thing, yeah, order matters because one's president and then in another arrangement they're not. So I'm going to have to go with a permutation on that one. And that's how you really have to decide. So let's ask you another question. We'll come back and do subsets and then we'll be done. All right, nice work. Now the last bit, subsets. This is a different type of counting. It is that there are 2 possibilities. Either we're going to include this thing or we're not, and that's it. I'm just going to keep multiplying really by 2. I'm going to multiply this by 2. Are we going to do that? Yes or no? There's 2 outcomes, yes or no. Are we going to do this one? Yes or no. 2 outcomes. This one? Yes or no. 2 outcomes. We're going to multiply together and see how many are. And end of story. So if you look at my example, and you'll notice here too, by the way, the formula for that is 2 to the n. That's how many subsets you will have in your outcomes. So we go to an ice cream parlor. They have 6 different toppings. How many ways could you select toppings, right? You go through and I just want sprinkles. Well, the next guy could go through and go, I want sprinkles and Snickers and marshmallows. And you're like, ooh, wow. So there's already 2 outcomes. Well, there was 6 different toppings, right? And so the next guy's like, well, I want jelly beans. And I'm like, ooh, there's another outcome. And another person's like, I want sprinkles and jelly beans. We're like, dang it, there's another outcome. How many are there? Well, if you think about it, there's 2 outcomes for sprinkles. You're either going to have them or you're not going to have them, right? There's 2 for marshmallows. You're either going to have them or you're not. And there's 2 for, what else did I say? I don't remember. Chocolate chips. That was one. And then there's 2 for the next time. And so you have all 6 toppings. You have 2 choices. You're either going to put them on there or you're not going to put them on there. And if they're all nots, then, there's your empty set. And you didn't put any toppings. Good job. That's still an outcome because you chose not to do anything. So I have 2 times 2 times 2 times 2 times 2 is 2 to the 6, which is, what is that? 2, 4, 8, 16, 32, 64. That is 64. There are 64 different ways that we can select toppings at Menchie's if they only decide to have 6 toppings out. Now we all know Menchie's has a lot more. So let's go get an ice cream. Have a great day. Stay happy, and I'll see you tomorrow.